Swayam Prabha. Digital India. Educated India.
We talked about tail bounds in great detail. One might ask a question: if there is central limit theorem, why did not use central limit theorem? The central limit theorem essentially tells you the sampling distribution converges to standard normal distribution when you scale the variables, when you center and scale the variables appropriately. So, if I have normal distribution as a resulting limit, why would I not compute the tail bounds using this limit? There are problems. So, the reason we developed many of the bounds, namely Markov, Chebyshev, Chernoff, Hofding, Bernstein, cannot be obtained from central limit theorem. So, this is a technical aspect of tail bounds and its relation to central limit theorem, and it is a topic in probability theory. So, I would like to give you a preview of this result. So, let us start with the Bernoulli variable. A random variable is said to be a Bernoulli variable if it takes 0, 1 value. It takes 1 with a probability p and 0 with a probability 1 minus p. Let x1, x2, xn be IID samples of x. X is a Bernoulli random variable. I am considering a sum I is equal to 20 and xi. Let S be a random variable whose value lie in between the interval 0 to n. Please understand, i's are xi's are going to take a value 0 to 1. So, S is a random variable whose value lie in the interval 0 to n. So, I would like to ask myself the following question: what is the probability that this random variable S, which is the sum of all the random variables, random samples xi, I is equal to 1 to n, which is Sn. So, S is equal to Sn is equal to k. What does it mean in terms of colloquial language? What is the probability that in n tosses I will get k heads, and that gives you that is a binomial distribution, that is n c k p to the power of k 1 minus p to the power n minus k. We already know expected value of xi is p, variance of xi is p times 1 minus p. The expected value of S is np, the variance of S is n times p into 1 minus p. So, what is that we have utilized in here? The xi's are IID. For IID variable, the mean is the sum of the means, the variance is the sum of the variance. Now, this random variable xn is now going to be transformed. I am going to subtract the mean, that is called centering. I am going to divide it by the square root of the variance, which is the standard deviation. So, this is the centered scaled variable, centered scaled variable. I am calling it Zn. So, if I set np is equal to mu and sigma square is equal to np times 1 minus p, this will look like the standard transformation. So, these two look alike. Clearly, I would like to be able to ask a question: what is the probability that Sn will be less than or equal to u? Now, we know from here Sn is equal to sigma Zn Zn plus mu. So, these two events are exactly the same. I can also have rewritten that Zn less than or equal to u minus mu by sigma. So, I am interested now in the distribution of Zn. Let us consider a special case p is equal to half, that means it is a symmetric coin tossing. In this case mu becomes n by 2, the variance becomes n by 4. So, the standard deviation is square root of n by 2. So, my Zn when p is equal to half now takes the form, if you simplify this, 1 over square root of n summation I is equal to 1 to n 2 xi minus 1, and that is equal to 1 over square root of n eta I is 2 xi minus 1. So, this random variable eta I, by virtue of the fact xi takes 1 or 0, if this takes a value 1 minus 1 is the probability half. So, you can think of Zn as a scaled random variable. We have already seen this is a kind of a red marker variable, minus 1 plus 1 with an equal probability. Now, for any integer k to any integer k in the range 0 to n, I would like to be able to ask a following question: Zn must be less than or equal to 2k minus n divided by square root of n, and this probability is essentially nck 1 over 2 to the power of n. Please understand, 1 over 2 to the power of n minus 1 over 2 to the power of k times 1 over 2 to the power of n minus k. So, is 1 over 2 to the power of n, and that is the probability of Sn being equal to k. Please understand, these are two events. A plot of this probability as n tends to infinity converges to the belt shaped Gaussian distribution with the 0 mean and unit variance. So, here is a good simulation exercise. So, what is that I would like you to do? I would like you to pick n to be very large, let us say 500 or 1000. Conduct this experiment, sample, compute this probability and plot it, and increase the value of n. See how the binomial plot tends towards the standard Gaussian. So, what is the goal in here? I want to understand the rate of convergence of this distribution, sampling distribution, to the target, namely the standard normal. We do know the limit is standard normal, but I would like to understand how fast does it tend to the limit. So, I am interested in the rate at which the convergence takes place. So, what is the contents of central limit theorem? If z is a standard normal variable for any sequence of independent identically distributed random variables x1, x2, xn, not necessarily binary valued, as n tends to infinity we have Zn tends to z, in the sense that for any u, probability Zn less than or equal to u tends to probability z less than or equal to u. That means this is the target limit, this is the sampling, and this happens as n tends to infinity, Hey, that's the contents of the central limit theorem. Please understand, z is a standard normal variable, that is what is involved in here, the right hand side. On the left hand side, what is that involved? I have x1, x2, xn. We introduced the notion of a binary value random variable, but this theorem holds good even if it is not a binary random variable. But we can even assume it is just a binary random variable, and we have already defined Zn earlier. The Zn that we defined earlier tends to z, and that is the essence of the central limit theorem. And what is the meaning of that? The probability that Zn less than or equal to u, that is an event, that probability tends to, in the limit, the normal random variable z less than or equal to u. And what is this probability? This probability is essentially 1 over square root of 2 pi integral minus infinity to u exponential minus x square by 2 dx. In our one of the notations, we call it phi of u. That is a cumulative density. That is a cumulative density. If this is u, this is the cumulative density, the area under the curve from minus infinity to u, this is u, from minus infinity to u. So, that is the area under the curve. More specifically, for every epsilon, so mathematically speaking, this is a way to say it, there exists an integer n such that for all little n greater than capital N, that means the little n is larger than capital N, and for every u belonging to R, probability of this event, which is based on n samples, the probability of n event, this is based on standard normal distribution, the difference between this probability, the absolute value of the difference will be less than epsilon. So, now you can see how large n should be in order that this probability is less than epsilon. That depends on capital N, the n must be greater than capital N. So, n depends on epsilon, capital N depends on epsilon. Our goal is to understand this error. Our goal is to understand this error as a function of n, this error epsilon as a function of n. That means, I want to understand how fast epsilon goes to 0. Recall, z is equal to normal 0 1, if y is equal to normal with mu as the mean and sigma square of the variance, z is equal to y minus mu by sigma. If z belongs to RD, is a standard normal vector in d dimension, phi of z is circularly symmetric. Why phi of z is circularly symmetric? I want you to be able to look at the circular symmetry. If z belongs to RD and if z is normal 0 identity, P of z you should know by now is square root of 2 pi d by 2, the determinant of I times to the power half, which is 1, times exponential minus 1 half, the mean is 0. So, x transpose I inverse transpose x, but this is essentially x transpose x. So, this is equal to minus 1 half x transpose x, minus x transpose x is equal to minus 1 half summation xi square, I is equal to 1 to d in this particular case. So, I can also write this as minus 1 half the square of the norm of that. The square of the norm of that is circularly symmetric. That means, the set of all x which has a common length, they are all, so the square of the this is equal to c. So, there is a rotational symmetry in here, there is a rotational symmetry in here. So, that is the basic property of the probability distribution. Now, I am coming to a basic result in probability theory called Berry-Essen theorem, BET for short. It strengthens the central limit theorem. Generally, in a course on probability theory, they do not cover this, because central limit theorem was proved very, very early, and people were interested in trying to quantify the rate of convergence, because they would like to be able to understand, can we use central limit theorem to quantify probabilities of events when n, the number of samples, is finite. If I can use the central limit theorem to find for finite n, I could use this approach to be able to get tail probabilities, but there are intrinsic difficulties. That is the reason we approach the tail bounds by different methods. So, that is what I am now going to reinforce. So, Berry-Essen theorem, let x1, x2, xn be independent, and with a loss of generality we assume they are all mean 0, and they all have a variance, xi has a variance sigma I square. So, they are independent, they need not be from identical distribution, but the distribution has a property that the expected value is 0, the variances are different. and I am assuming that the sum of the variances is 1. If the sum of the variances is not equal to 1, I can scale the variables, and this can be obtained very easily simply by the mathematical trick of scaling. So, let us assume I have a bunch of scaled independent sequence of random variables. I did not specify that distribution, I only specify the first moment. The first moment is 0, the second central moment depends on I. I am assuming for the chosen n, the sum of the variances is equal to 1 because of scaling. Then for all u belonging to R, that means for every real number, now look at this now. What is S? S is a scaled version of the sum. So, what is this? S is equal to here, and the difference between the probability S less than or equal to u minus Z less than or equal to u is less than or equal to a constant multiple times beta, where beta depends on the sum of the expected value of the third moments of the individual random variable, and Z is the standard normal random variable. So, when I say O1 means what? This is the constant. This is the constant. This constant, it can be shown in the paper, is 0.514. Is a small constant, roughly equal to half, in the neighborhood of half. Please understand, Beren-Essay theorem does not require us to be identical. So, if it is identical distribution, there is an additional thing I should be able to utilize in here, in which case sigma I square will all be sigma square. So, now you see the essence of the convergence result. So, S is the random variable that represents the sum is less than or equal to u, Z is less than or equal to u. This is the sampling distribution, this is the normal distribution. The difference between them is a function of the sum of the third absolute moments of the random variables in question. Please understand, this is not epsilon, that is what we wanted to have, and that is a hidden constant. The constant is about half. So, I would like to, I am not going to go into the proof of this theorem right now. I would like to understand how the bound works. In order to understand how the bound works, let us concoct a random variable xi is equal to 1 over square root of n with the probability half minus 1 over square root of n with the probability half, and they are independent random variables. Variance of xi is 0, variance of mean of xi is 0, the variance of xi is 1 over n, you can very easily check. So, I am trying to consider a sequence of random variables whose mean is 0, whose variance is 1 over n, where n is the number of samples. So, the variance of Sn is equal to the sum of the variances of xi because they are independent. So, n times n is equal to 1. So, the variance of Sn is 1. The mean of Sn is also equal to 0 because xi's are 0. Now, I would like to be able to compute the third moment. The third moment of xi with this distribution, you can readily see 1 over square root of n cube times half minus 1 over square root of n cube half, because the mean I am interested only the third absolute uncentered moment, and if you simplify this, you find this to be n to the power 3 by 2. And what is beta? Beta is the sum of the expected value of the third absolute moments. Each of them is equal to n to the power of 3 by 2. There are n of them. So, if you multiply this, you have 1 over square root of n. Wow, that is very interesting. Now, look at this now. In this bound in 1, the difference between the sampling distribution and the limiting distribution is upper bounded by a constant which is about half times beta. Beta is the sum of the third moments. I did not prove this theorem. I am taking this theorem is very well established, well known. There are proofs in many standard textbooks. One of the books I like is Feller, William Feller, volume 1, probability. The 2-volume books by William Feller is a great book, Feller. Volume 1 and 2, William Feller. Cheap editions, Indian editions are available. If I have any difficulty in probability theory, I always fall back on this book. It's a great book to have. So please try to get good books on probability theory and have it ready for quick reference. So what is that we are now we have found out? We have applied the essence of Berry-Essen theorem to a particular random variable we chose to show the convergence is of the order of 1 over square root of n. Wow, that is very interesting. 1 over square root of n is a slow convergence. That means for all u belonging to R, the absolute value of the difference between the sampling event and the limiting event is less than or equal to 0.56 divided by square root of n. That is 0.56 divided by square root of n is the rate of convergence, and that rate is very low. If n is 100, it reduces to 1 over 10. If n is 10 to the power of 4, it reduces to 1 over 10 square. So to get the rate as 1 over 10, I need 100 samples. To get the rate as 1 over 100, I need 10 to the power of 4 samples. That is the challenge. So the whole question comes in, can this rate be improved? Now we are, in other words, so what is that we have done? We wanted to see if I could have used central limit theorem to derive the tail bounds. If you give me the normal distribution, which is the limiting distribution, I can compute all the tails, which we have already done. The question is, why didn't we not use them? This normal distribution is only in the limit. So when I have, and the limit theoretically attains only when n is infinity. So when I am in the intermediate range of finite n but not too large, what do? Can I apply the results of this theorem? The answer is no, because it has not converged. If it has not converged, there will be error in the estimation. That is the reason why we did not use that. Now we would like to be able to understand, can we improve the Essen theorem to salvage the problem? What is the problem? Can I use the limiting distribution to compute the tail bounds? So to that end, I am assuming n is even, and let S be a random variable, which is the difference between the number of heads and number of tails divided by square root of n. When S is 0, the number of heads is equal to number of tails is equal to n by 2. Please, I have n tosses. So to estimate the probability using 1, let epsilon be 0, then the probability the number of heads is equal to number of tail is the same as probability that S is 0. Which is the same as probability S less than or equal to 0 minus probability S less than or equal to minus epsilon. So look at this now, this is 0, this is epsilon minus epsilon, 0 minus epsilon. So this picture essentially helps you to be able to visualize this. So this quantity now becomes this, which is probability S less than or equal to 0 minus probability less than or equal to Z is less than or equal to less than or equal to 0. So this is the event, this is the normal distribution. So, what is that I am trying to do? I am trying to express this by manipulating this expression, Here is probability s minus 0, this is probability z minus 0, this is the target I want. This term remains here, minus probability z less than or equal to minus epsilon. So, this event equal to this event, which is equal to this difference, which is given by this expression. You can readily check that, plus this. So, what is it we are trying to do? We are trying to add and subtract. Look at this now. This is subtracted, this is added. This is subtracted, this is added. So, these two terms cancel each other, these two terms cancel each other. So, the difference of two terms is expressed as the difference of three pairs of terms by the simple trick of add and subtract. Therefore, nothing has changed except that I have details in the expressions. Details in the expression. So, what is it I want? I want to be able to compute the difference. So, the absolute value of the difference of the first term. Look at this now. I am having this event. I am talking about that event expressed as a sum of three quantities. Now, if I took the absolute value, I am trying to inflate the right hand side. So, the equality becomes an inequality, and this is the difference we are looking for. Look at this. I am looking at the absolute value of this, and I can combine the two terms, and this is equal to probability minus epsilon less than z less than or equal to 0. So, look at that. This is the reason why we added and subtracted. So, the quantity, that probability, the number of heads is equal to number of tail, is less than the sum of these three probabilities. Now, when epsilon tends to 0, so what is 0 plus? I want you to understand the notion of 0. When you say epsilon tends to 0 plus means what? Epsilon tends to 0 while remaining positive. That means epsilon reaches 0 while remaining positive and moving towards, so 0 plus. Likewise, there is also a concept of 0 minus. Epsilon can tend to 0 minus means what? Epsilon remains negative, but tends to 0 from the left side. 0 plus means what? The epsilon remains positive and tends to 0 from the right side. So, I am keeping epsilon positive, but smaller and smaller. Therefore, the probability then of number of heads is equal to number of tail is less than or equal to the first term, first term. This is the second term. The third term tends to 0 where epsilon tends to 0 plus. So, I can drop this term because this tends to 0. Now, the second term, absolute value of probability s less than or equal to minus epsilon, z minus epsilon. Now, look at this now. This comes under BET, Berry-Essen theorem. So, by Berry-Essen theorem, this is 1 over square root of n. This is I am sorry, 1/2 of 1 over square root of n, 1/2 of square root of n. The sum of the two is 1.12 by square root of n. So, this is something we used Berry-Essen theorem to compute. I could have computed this using the binomial distribution. The number of heads is equal to number of tail, that is equal to NC n by 2 by 1 over 2 to the n. When n is large, I can approximate n by Stirling's approximation. So, NC n by 2 is factorial n divided by factorial n by 2 whole square. factorial n by 2 whole square, that is what is given in here. So, I use the formula, I combine the thing. So, I go from here to here. I can express everything in terms of the Stirling's approximation, which when I simplify gets this, which is 0.798 divided by square root of n. So, this is the exact value, that is 1.12 is an upper bound. These two upper bounds have the same rate of convergence square root of n. So, what does this tell you? There exists one distribution for which the Berry essence limit is attained. If I can show for there exists one distribution for which this limit can be attained, we do know we cannot improve that. Therefore, the hope of improving the Berry essence theorem is impossible. So, let us come back. Why we did the detour? Again, I want to re-emphasize. I want to explore why we could not have used central limit theorem to get the tail bounds. That is because now we have shown that Berry essence theorem essentially tells you the convergence is slow is the order of 1 over square root of n. But if you look back our Chernow bound, we had exponential bounds. Exponential bounds are much stronger than 1 over square root of n. So, I would like to get much stronger bounds than 1 over square root of n tends to give us. So, we now come back to the notion of tail bounds. Again, I am going to quickly illustrate some of the ideas of the tail bounds. X is equal to summation xi, head or tail plus or minus 1, probability half-half, tosses are independence. You can think of this as the Rademacher random variable. What is the probability S deviates from the mean? EF is equal to 0. The mean of xi is 0, the mean of S is 0. So, I would like to be able to compute what is the probability that S deviates from the mean. F deviates from the mean what? I am interested in the tail probability. The deviation from the mean is equivalent to the tail. So, more specifically, I would like to find out what is the probability S greater than t, that is a tail probability. We expect this to be small for a large tree. We want this quantity, we want to quantify it by deriving an upper bound. That means, I want to be able to get an upper bound on PF, on the even probability that S greater than t. By Berry essence theorem, probability that S greater than or equal to square root of n t minus probability G greater than t. What is G? G is a standard normal distribution, that is what I am assuming now. Sometime I call it Z, sometime I call it G, that should not bother anyone. By Berry essence theorem, this is the constant times 1 over square root of n. So, instead of carrying that 0.55 so on, I am simply calling it a constant. You could have replaced it C by C over square root of n, where C is a constant less than 1. So, this essentially tells you the probability that S greater than or equal to square root of n t is equal to, I am going to take this other side, probability that G greater than or equal to t plus or minus constant times 1 over square root of n. So, the transition from here to here is simple algebra. Verify. Now, I can compute the probability that the Gaussian random variable takes a value greater than or equal to t. So, probability G greater than or equal to z 0 to infinity 1 over square root of pi, the standard Gaussian variable. But this is less than a constant time e to the power of minus t square by 2. Okay. I would like you to be able to evaluate this integral and show this integral is less than the constant multiple of e to the power of minus t by 2. You should be able to do that. We have done similar inequalities when we talked about Markov inequality. So, the least value of x it can take is t So, this is an exercise for us to verify. Now, t is a variable I am going to have to choose. So, I am going to choose t is equal to 10 to the power square root of log n. So, I am now going to combine this term which is given by here, which is bounded by here, and I chose a particular t. So, combine 4 and 5, what is that? The event, the probability event s greater than or equal to square root of n times t is equal to square root of probability that g greater than or equal to t plus order of 1 over square root of n. So, look at this now, order of 1 by square root of n can be written as simply order of 1 over square root of n, order of square root of n, and that is what it is this. So, by the right hand side of phi, I can see this term is equal to that. This comes from the inequality of phi, and this comes directly from Berry-Essen theorem. If you simplify this, you can readily verify. Please understand that is 10 square root of log n square divided by 2. You simplify this, the very nice algebraic simplification. I am going to leave it as an assignment for you. So, this is the order of 1 over n to the power of 50 plus 1 over square root of n. N to the power of 50 goes to 0 very fast, but you all know the strength of the chain is that of the weakest link. So, this is the horse that runs slow, this is the horse that runs fast. In looking at the rate of convergence, I have to look at the horses that run slow. The slow horses is going to dominate the show. Therefore, the overall order of convergence as n goes to infinity, this term goes to 0 much faster than this term. So, he is the dominant term, and that is the dominant rate of convergence. This essentially tells you the tail of the Gaussian. So, what does it tell you? The tail of the Gaussian goes to 0 very fast, but the convergence of the sampling distribution to the Gaussian takes a longer time. So, this again tells you the BET bound cannot be improved. BET bound cannot be improved. So, these are all kind of negative results, but these negative results are important to understand tail bounds, to understand why we do what we do, why we do not use something else. And the mathematics of this is absolutely good mathematics. By doing this, you understand the analytic approach to probabilistic arguments. Please understand, I have not proven Berry-Essen theorem. So, once you understand the proof, now you understand the importance of Berry-Essen theorem. That should motivate you to go back to understanding the proof of Berry-Essen theorem. It is an old theorem, but it is a very important theorem. Now, I am going to quickly run through maybe second time for the sake of completeness, using the same idea, using different formalism. I am going to go back to Markov inequality. Markov inequality uses only the mean. Theorems, I am going to call it theorem 7. So, Markov inequality can be looked at. X is a non-negative random variable, x is greater than t times e to the power of x, I am sorry, t times expected value of x is less than or equal to 1 over t, and this can be easily seen. This is the Markov inequality we have already proved. So, if I set alpha is equal to t e x, this inequality now becomes this. So, this is another way in which Markov inequality can be expressed. Only to be able to emphasize that, I am doing the same Markov inequality in a slightly different notation, and that is important. So, let xi be plus or, I am going to give an example. Let xi be equal to plus or minus 1 with a probability half-half. S is again the sum of xi. S now belongs to the interval minus n to plus n. Expected value of S is 0, variance of S is n. These are all standard things that come from basic probability theory. I would like you to verify. Now, t is equal to s plus n. If t is equal to s plus n, you can readily see s belongs to minus n to plus n. So, if I add n to that, t is always positive. E of t is equal to E of s plus n. So, while the expected value of s is 0, the expected value of t is n. Now, I am going to pick my little t to be 10 times square root of n log n. See, the reason why I am doing this, it is this trick. What is t? T is a threshold. What is the probability that the random variable x will be greater than the threshold t? Now, by picking the different values for the threshold as a function of n, the number of samples, I can get beautiful illustrations to show the power of the conclusions of Markov inequality. That is the reason we are doing what we are doing. So, we are not simply stating is greater than or equal to t, we are giving an expression for t which is a function of time, which is an increasing function of time 10 times square root of n log n. Now, you all should know n log n goes to infinity as n goes to infinity. So, probability that s greater than or equal to t is the same as probability the random variable transform random variable capital T is greater than or equal to t plus n, and that is equal to t greater than, look at this now, I am multiplying t plus n by n and dividing by n, but we know expected value of t is n. So, I can say E of t times t plus n divided by n. Please understand, if I have x, I can say x plus a minus a. If I have x is equal to a times x by a. So, add and subtract, multiply and divide, these are all standard tricks, and these are all the tricks you need to be able to understand along with the rules of probability theory, and this by virtue of Markov inequality is n over t plus n. Now, t is 10 times square root of n log n. So, if I divide numerator and denominator by n, this becomes 1 divided by 1 plus 10 over n square root of n log n, 1 over square root of n log n. Now, you can readily see 10 over n square root of n log n is equal to 10 over square root of n log n divided by n square, which is equal to 10 over square root of log n divided by n. You should all know log n divided by n goes to 0 as n tends to infinity. Therefore, this term 10 times this goes to 0 as n goes to infinity 1 by 1. So, that tends to bound 1. So, this does not converge to 0. You can readily see this does not converge to 0. So, what is that we have said? We have given an example where the bound is very loose. So, there are examples for which it is tight. I have already shown an example earlier. Here is an example that tells you it can be loose. Now, again I am going to go back to revisit the Chebyshev bound. Here I use the mean and the variance. This is the expected value, this is the variance. So, the Chebyshev inequality essentially tells you probability absolute value of x minus mu greater than or equal to t sigma is less than or equal to 1 over t square. That is another way in which Chebyshev inequality can be written, and that is one of the reasons why I am doing this again. So, if I say y is equal to x minus mu whole square, which is a positive random variable, the variance of x is sigma square, which is equal to expected value of x minus mu whole square. So, the probability that the absolute value of x minus mu is greater than or equal to t times sigma is the same as squaring both sides, which means it is the same as y is greater than or equal to t square times expected value of y, which is 1 over t square. So, we can readily see this is another version of the way in which I can express Chebyshev bound. We need to be able to rewrite these inequalities in different ways. That is the reason I am talking about each of these. Now you may wonder, why should I worry about all these things? Please understand, you cannot compute tail bounds without having good ideas about Markov inequality, Chebyshev inequality, Chernoff inequality, and so on. And why do we need tail bounds? Because we are interested in measure concentration, and measure concentration occur naturally in high dimensional spaces, in high dimensional probability theory. That is the reason. So, if you want to be serious about multidimensional probability with respect to multidimensional data analytics, these are important tools and techniques. So, I am now going to illustrate it again. Xi is equal to plus or minus 1 to the probability half. Again, S is equal to Xi, I is equal to 1 to n, mu is 0, variance is given by n is equal to sigma square. So, the standard deviation is square root of n. I know I am going fast, but these are routine things. We have already done several of these things many times. So, again I am going to find out the probability of the event S greater than t, t is 10 square root of n log n. So, this is equal to this probability less than absolute value of S greater than or equal to 10 times square root of n log n, but this quantity is equivalent to absolute value of sigma times square root of n log n. I am multiplying dividing by sigma, and this by Chebyshev inequality now becomes sigma square by square of 10 square root of n log n, which is n over 100 n log n. This is 100 over log n, and that goes to 0. So, this goes to 0. So, this is not as good as expected, because we want, but still it goes to 0. It is good. It goes to 0, but it goes to 0 at again a slow rate, 1 over log n. So, 1 over square root of n, 1 over log n. I want you to understand the rate of convergence. So, what is a good exercise for you? Plot 1 over n, plot 1 over square root of n, plot 1 over square root n square, plot 1 over log n, plot 1 over n log n, all against the same graph versus n, and try to compare. Each of these terms have to go to 0. Compare the rate of decrease of these, and these do not decrease as fast as exponential. So, e to the power of minus t as a function of t goes to 0 much faster than many of these things. So, we are interested in faster convergence. So, that is why this is not as good as expected, because it converges only as 1 over log n. The derivation needs only this derivation needs only pairwise independence of xi. So, that is a technical term, and so there is a question of mutually independent, pairwise independent. Pairwise independent means every pair is independent. Mutually independent means any collection of a subset of k random variables are independent. So, mutually independent is much stronger than pairwise independence. So, variance of S is equal to variance of x1 plus x2 plus xn is equal to expected value of this square of the sum minus square of the expected value. Square of the expected value is 0. So, the expected value of this is simply square of xi's plus square of the cross product. The cross product terms are 0 because they are independent, pairwise independent. So, this is where the pairwise independent comes into being. Why? This comes from a plus b plus c whole square, that depends on a square plus b square plus c square, 2ab, 2bc, 2ca. So, there are pairwise product, and this is 0 because of independence. Because of independence, the product of expectation is the expectation of the product is the product of expectation, and the individual expectations are 0. You can see how very many different facets are applied in here. This is the sum of all the variances, and that is n, which we have already seen. Now, I am going to compute the fourth moment method. So, let S be a random variable which is the sum. I am interested in s to the power of 4. S to the power of 4 is a normal, non-negative random variable. So, my Markov s greater than equal to 10 times n log n, square root of that, is the same as s to the power of 4 greater than equal to 10 times square root of n log n to the power 4, which is by Markov inequality. This is expected value of s to the power of 4 divided by 10 to the power of 4 n square log square f n. Now, I am going to quickly estimate s to the power of 4 to tell you. You remember we talked about using first moment only Markov, using first moment and variance Chebyshev. Now, we are using fourth moment to be able to obtain bounds, tail bounds. So, E of s to the power of 4, there is a fourth power of the sum. This is equal to sum of all the fourth powers expected value plus squares of pairwise the product of xi with xi cube plus xi xj xk square plus xj xj xk x cube. So, this consists of first term, second term, third term, fourth term. Algebra is simple. There is room for errors. So, I would like you to be able to be very careful. Here summation over I, j not equal to I, summation over I, j not equal to I, k not equal to I and j. Again, j not equal to I, k not equal to I and j, q not equal to I, j, k. All this algebra is very helpful, very useful. By independence, Ex is by independence and Ex is 0. Independence means what? Expectation of the product is a product of expectations. So, you can show these terms are zeros, these terms are zeros, and these terms are zeros. Leaving behind, I am only the fourth power term and the product of the square terms. The product of the square terms is the expected value of the individual square terms. So, this is equal to n expected xi to the power 4 is 1. So, I have computed this from here to here, and this is 3 times n minus 1, because the 3 comes in here, which we already know how we got it from there. So, this is 3 n square minus 2 n, which is less than 3 n square. Therefore, if I put 6 and 8 together, probability that s greater than 10 times square root of n log n is less than or equal to 3 n square divided by 10 to the power of 4 n square log n square, which is essentially 3 over 10 to the power of 4 log square n. This bound is better than Chebyshev bound. Please understand, Chebyshev bound, it reduces 1 over log n. This is reduces by 1 over log n square. So, this is better than Chebyshev faster convergence. So, we can extend it to 2kth moment by picking k and optimizing the upper bound with respect to k. By optimizing the upper bound with respect to k. Okay. But this requires estimation of e to the power expected value of s to the power of 2k, which can be more demanding. So, now you now know some of the difficulties and the implications of Markov, Chebyshev, and the kth moment bounds. Some of you may think that this looks like a course in probability theory, but please remember, the aspect of the probability theory is applicable to data science. So, now I am going to go over to quickly Chernow bound, which I have already done Chernow bound, but I am going to do it with this new point of view. So, instead of s to the power 2k, so we did s to the power of k. So, we did first moment, second moment, kth moment. We said we could have done it for any 2 to the power of k moment. I am sorry, any 2kth moment. But instead of this, in Chebyshev, I am sorry, in Chernoff, you consider exponential e to the power of lambda s, where lambda is positive. E to the power of x is an increasing function. So, expected value, I am sorry, the probability of the event s greater than or equal to 10 times square root of n log n, I can multiply. If lambda is the positive quantity, there is a result. If a is greater than b, if x is greater than 0, I can multiply x a is greater than x b. If you multiply an inequality by a positive constant, inequality remains the same. If you multiply an inequality by a negative quantity, the inequality reverses the sign. E to the power of x is an increasing function. So, if I first multiply by lambda and then taking exponential. So, the probability of this event is the same as probability of this event is the same as probability of this event. Now, I am going to apply Markov, which gives rise to this band. Due to the independence of xi's, e to the expected value of e to the power of lambda s is expected value of the sum. It is simply expressible as the expected value is the product. Now, you know, because you already know e to the power of lambda x plus y is equal to e to the power of lambda x times e to the power of lambda y. That is the thing that is being used in here. The expectation of the product is the product of the expectations. Now, I want to be able to compute e to the power of lambda xi. Xi's are plus or minus 1 is the probability half-half. Therefore, e to the power of lambda xi is essentially 1/2 of e to the power of lambda, 1/2 of e to the power of minus lambda. You expand this by a series, you expand this by its corresponding series. You cancel the term that positive and negative, you get a sequence in like this. You can readily see this sequence, this sum is less than e to the power of lambda square by 2. Please understand, e to the power of lambda square by 2 will have constant term, lambda square term, lambda square. So, what is e to the power of lambda square? This is going to be equal to 1 plus lambda square by 2 plus 1 over factorial 2 times lambda square by 2 whole square plus that. So, you can really see this bound is arrived from the expansion of e to the power of lambda square by 2, combining these expected value. Now, please understand what is this? This is the moment generating function of s. So, there is a product involved. So, this is the product of e to the power of lambda square by 2, which is equal to e to the power of n times lambda square by 2. From 9, we already know the bounds. So, let us go back to 9 to get the bounds. So, this is the Markov bound. Please understand, the ideas, there are not too many basic ideas. This is the Markov inequality. I am interested in the tail bound. So, by 9, which is the Markov inequality, e to the power of lambda s greater than or equal to e to the power of 10 times lambda square root of n log n. This is the event I am considering. The probability of the event is less than or equal to e to the power n lambda square by 2 minus 10 times lambda square root of n log n square root of n log n square root of n log n. So, that is the bound on the tail probability we got. So, if I set lambda, so I want to find the behavior of this. Now, lambda is a real number. So, I am now going to set lambda is equal to 10 times square root of log n over n. Please understand, we have choice, we have a lot of freedom. How you exploit this freedom is what we are after. So, lambda is equal to 10 times square root of log n by n is the one that minimizes the right hand side of 11. That again, I want you to be able to consider this. So, consider the function g of n, which is equal to n e lambda square, I am sorry, which is n lambda square by 2. So, this is the function of not n, but lambda, sorry, minus 10 lambda n log n. This is the quadratic function of this is the quadratic function of lambda. So, you can take lambda as a common factor. So, you can readily see I do not want to say lambda as a common factor, it is a quadratic in lambda. By computing the differential coefficient of g lambda with respect to lambda equating to 0 and computing the second derivative and checking it is positive, verify that lambda is equal to 10 times square root of log n by n is the one that minimizes the right hand side. And that is a principle that comes from Chernoff bound. So, Markov, tail probability, Chernoff bound, trying to optimize the bound with respect to the chosen parameter lambda. All these ideas are beautifully interwoven. I know I am doing it for the second time, but in a slightly different setting. So, both the ways of doing this should be able to help you to visualize the tools, techniques, the freedom, and how to exploit the freedom to be able to get what we want. Please understand, mathematics is a man-made science. It is how intelligent you are going to be able to make things happen, and that is the way it comes in here. Therefore, the tail probability is less than or equal to, with this particular lambda, I would like you to verify this is 50 log n minus 100 log n, and that when you simplify is going to be equal to 1 over n to the power of 50. So, we can use the same pathway for a general random variable. So, I have obtained the tail probability which can which the bound is much better. You remember earlier we showed n to the power of 1 over n to the power of 50 plus 1 over square root of n. The 1 over square root of n was dragging by the Berry essence method. Now, we got out of the Berry essence method and computed using the moment generating function, but before we consider the moment generating function, we consider the kth moment. So, Markov inequality based on first moment, Chebyshev inequality based on second central moment, generalization of Chebyshev using kth moment, which is the further improvement of Chebyshev. Then the ultimate generalization comes, instead of computing the kth moment or 2 kth moment, we are going to go for the goal, which is the moment generating function. We bounded the moment generating function, which gave rise to a much better bound. So, the idea is I got the Chernoff bound, IID random variables, expected value of xi is pi, the random variable takes 1 or 0 with the probability p1 minus p, therefore, expected value is pi. I am considering the sum I is equal to 1 t n xi, that the sum random variable is x, mu is equal to e of x. Then for any delta greater than 0, probability that x is greater than 1 plus delta times mu. So, what is that I would like you to do? I would like you to think of this as mu, this is 1 plus delta times mu, this is 1 minus delta times mu, this is the interval of concentration. So, I am going to look at the tail, which is above 1 plus delta mu, which is in this case it must be less than or equal to 1 minus delta mu. So, these are the two tails. The two tails can be given by this expression on the right hand side and the right hand side. So, this is the theorem now. based on Chernoff bound. This claim holds even for xi is uniform interval 0 to 1 instead of being Bernoulli. For delta in the open interval 0 to 1, this implies that x greater than or equal to delta x greater than or equal to 1 plus delta mu is exponential minus mu square delta square mu by 3, and this is less than or equal to, this is the other bound. So, this is called the upper inequality, this is called the lower inequality. We only need to prove the upper bound. The upper inequality, when I say upper bound, both are upper bound, but upper inequality. So, for lambda greater than 0 by Markov, this event is the same as this event. This probability by Markov is given by e to the power of lambda x by e to the power of lambda into 1 plus lambda to the power mu. Now, I am going to compute explicitly the moment generating function for xi, which is given by pi e to the power of lambda. The xi takes 0 or 1, when it is 0 is e to the power of 0 is 1. So, the moment generating function is given by this is 1 plus that, which is less than, please understand, 1 plus x is less than or equal to e to the x. Therefore, this 1 plus x is less than e to the power of x. Therefore, if I sum this over, that becomes a product, because e to the power of a plus b is e to the power of a times e to the power of b, same formula. Expectation of the product of expectations, expected value replaced by the formula that we have already given, and that is equal to expected value of e to the power of lambda minus 1 summation pi. Summation pi is mu in this particular case, please understand. We have already talked about that. Summation mu is summation pi, because each random variable has the mean pi, and mu is the mean of the sum. So, combining with 12, the probability that the upper is less than or equal to e to the power of mu times e to the power of minus e to the power of lambda minus 1 divided by exponential of this term. Now, I am going to set lambda. Please understand, lambda is a parameter. It is only to make you understand the trickery involved in here. I am doing this again like this. Lambda is equal to log of 1 plus delta, which is greater than 0. So, this essentially e to the power of lambda is equal to 1 plus delta. This is the index of the term in the numerator. This is the index of the term, one of the terms in the numerator. So, mu times e to the power of lambda minus mu is mu delta. These are simple exercises you need to check. Therefore, lambda times 1 plus delta times mu is equal to this, and that can be written as, now please remember, a log x is equal to log of x to the power a. I am using that formula in here. Therefore, this is equal to log of that. So, e to the power of lambda times 1 plus delta mu is equal to 1 plus delta to the power mu times 1 plus delta. Substituting this, we get the upper inequality, which is essentially the upper bound. So, we have proved a version of the Chernoff bound by confining our attention to binary random variables using Bernoulli distribution. So, this completes the derivation and further analysis of the power of Markov, Chebyshev, Chernoff, kth moment. Of course, there are other tail bounds, Hofding inequality, which applies to xi IID, where xi is bounded random variables. I am interested in bounding the tails of the sum of bounded random variables. Now, please understand, x is the sum of xi, xi's are bounded, each one are bounded in different intervals. They are only independent, they are not IID, they are only independent, because they are defined over different intervals. If all the AIs and BIs are the same, then it becomes IID. So, in this case, the tail probability that x greater than t plus E of x is less than or equal to exponential minus t square by summation bi minus ai whole square. We have already proved this earlier in concentration of measures using Hovding inequality. So, what does this tell you? If you have a random variable normal, how the tail behaves. If you have a binary random variable, how the tail behaves. If you have a bounded random variable, how the tail of the sum behaves. So, that is what the idea is. So, everything is relating to bounding the tail probability under various situations. Bunsen inequality again, xi's are IID random variables, they are bounded, uniformly bounded. I am interested in the sum. The expected value of each of them are 0. So, I am interested in the sum of independent identically distributed mean 0 bounded random variables. So, this is bounded mean 0, sum of that they are IIDs. So, in this case probability that the sum, the tail of the sum is again given by exponential minus t square divided by f(x) square plus 3mt. So, if the bound is large, m is large, this quantity is much smaller. Minus t square, if t is large, minus t square is also much smaller. So, this is the essence of it. Now, what is the summary? The summary is, I cannot use Berry-Essence theorem, even though I know the limit of the centered scale random variables for quite a variety of distributions tend to standard Gaussian, because the rate of convergence is very slow, 1 over square root of n. So, the whole discussion at the second level of the concentration tail inequalities is motivated by examining the relation with central limit theorem and our inability to use the central limit theorem to compute the tail probabilities because of slow convergence. In that process, we have relearned to do quite a variety of analytic techniques. It is simply for the richness of the analytic technique I decided to do this again in this format. So, with this we have quite a good dose of probabilistic analysis for concentration of measures. Hope you enjoy. Thank you. Bye.